Hello everyone, my name is Michael Baratko, and I will discuss our work, Min-Max Stability and Box Distributions. This is a joint work with Javier Baroni, Shib Sankar Dasgupta, and Andrew McCallum. Two of the most fundamental problems in machine learning are learning representations of data capturing relevant correlations for downstream tasks, and compactly modeling a joint probability distribution. A common solution to the first problem is to train vector representations. However, these do not have a natural probabilistic interpretation. On the other hand, graphical models are the standard approach to compactly modeling a joint probability distribution, but do not scale and generalize in the same way as learned representations do. Probabilistic box embeddings, introduced in Vilnius et al. 2018, are a novel region-based representation which handles both objectives. Rather than vectors, entities are represented using boxes, i.e. a Cartesian product of intervals, which can be thought of as a trainable Venn diagram of sorts. The volume of a box can be easily calculated, and boxes are closed under intersection. Box embeddings have successfully been employed for graph modeling, market basket style recommendation tasks, and even representing entailment by training deeper recurrent models to output a box. Box embeddings are trained using a probabilistic interpretation, which is possible when the boxes are embedded in a space with finite measure. In this toy example, we consider a subset of boxes capturing occupational information about people. The marginal probability of being an author is given by the volume of the author box, and similarly, the probability of being a biologist is given by the volume of the associated box. One can also calculate conditional probabilities, for example, the conditional probability of being an author given that one is a biologist. In fact, any combination of positive assignments can be calculated via intersection volume. And since the space has finite measure, inclusion-exclusion can be used to calculate any arbitrary assignment of values, such as the probability of not being a child, or the probability of being a biologist but not an author. While seemingly a minor detail, this latter point is actually critical. Even if we only wish to consider marginal volumes of single elements as proportional to probabilities, we must have finite measure on the space, or incompatible assignments may arise. This was easily accomplished in the original probabilistic box embedding model by parametrizing boxes to remain within the unit cube. Unfortunately, the original approach to modeling boxes suffers from issues with training. The hard edges of boxes lead to discontinuous gradients, and many regions with no training signal at all. The Gumball box model, introduced in Dasgupta et al. 2020, mitigates this issue as well as others by taking a latent random variable approach. The endpoints of intervals are modeled as Gumball random variables, and thus the model actually ensembles over a family of box models. Here we depict a one-dimensional Gumball box, where the blue curve indicates the probability of a point on the horizontal axis being inside the box. The Gumball distribution was chosen due to its min-max stability properties. Namely, the Gumball distribution comes in two variants, max Gumball and min Gumball. The max of two max Gumball random variables is once again max Gumball, and the min of two min Gumball random variables is min Gumball as well. The concept of min and max stability has other uses in the literature. However, we formalize the relevant aspects of min and max stability for our purposes, as shown here. The main reason to select min-max stable distributions is to preserve the property of closure under intersection. Namely, the intersection of two Gumball boxes is once again represented as a Gumball box. As described in our paper, this fact is what enables us to calculate arbitrary assignments of values to the binary random variables we are representing via inclusion-exclusion. This approach proved to train far better than the previous model, as the loss landscape is completely smooth. However, the resulting model could no longer be interpreted probabilistically. In particular, the Gumball variables modeling the endpoints of intervals are unbounded. Naively restricting these parameters to a bounded universe would still result in probability mass outside the bounded region. There are two possible solutions to this problem. One could use bounded random variables which are min-max stable, thus preserving the closure under intersection property, or alternatively, rather than bound the space, one could take the expectation using a probability measure on the real line. However, for any solution, we must also be able to analytically calculate the expected volume of a box. Ensuring that the expected volume is computationally tractable is most easily accomplished by taking the universe itself to be represented as a Gumball box, since we already know we can compute the expected volume of the intersection of Gumball boxes. In our work, we prove that this simple solution does in fact yield a valid probability model, rectifying the previous issues when interpreting the Gumball box model probabilistically. More interestingly, the resulting solution can actually be interpreted to fulfill both of the previous solutions. The box density can be interpreted as providing a finite measure on the real line, and also can be interpreted via change of variables as transforming the Gumbel distributions to min-max stable distributions on 0, 1. These three alternative perspectives provide several footholds for further analysis and expansion. The first allows for geometric intuition, while the second provides the justification of probabilistic semantics. In particular, our model is now able to learn marginals or arbitrary joint or conditional probabilities. Finally, the third interpretation yields interesting new families of bounded min-max stable distributions. Here we depict these transformations H for different choices of universe box, noting the similarity to the sigmoid function for certain choices of parameterizations. The characteristics of the bounded min-max stable distributions which result from applying this transformation will depend on the parameters chosen for this universe box. Transforming the Gumbel boxes using such a function h results in a novel set of distributions on 0, 1, which we call bounded Gumbel box distributions. Here we see the unnormalized densities, which represent the bounded Gumbel boxes in 0, 1. The green curve represents the intersection. The boxes on the right are wider than those on the left. And here we see the impact of high and low scale parameters on the universe box. As the scale parameter of the universe box goes to 0, we recover the original probabilistic box embedding model. To get a sense of the loss landscape in higher dimensions, we also plot the probability of a point being inside a two-dimensional bounded Gumbel box. We evaluate these bounded Gumbel boxes by modeling conditional and marginal probabilities based on movie lens, a dataset with movie ratings. As done in previous box embedding evaluations, we binarize the data and consider that a user liked a given movie if they rated it greater than 4. To ensure relevance, we filter the movies to those with more than 200 ratings. We then calculate marginal, joint, and conditional probabilities based on co-occurrence counts. We compare our model against other probabilistic representation learning models, including probabilistic order embeddings and probabilistic box embeddings. We train on conditional and unary marginal queries and evaluate on pairwise joint queries. Our model significantly outperforms the baselines, which is to be expected as it has greater representational capacity than probabilistic order embeddings and smoother training objective than probabilistic box embeddings. In this work, we introduced several families of bounded distributions, the bounded Gumbel box distributions depicted earlier, as well as the underlying min-max stable distributions which model their endpoints. We demonstrated that bounded Gumbel boxes are a probabilistically sound representation learning model and recommend their use for any task where trainable representations capturing properly calibrated probabilities are desired. This work also exposed 3 equivalent perspectives for understanding these new distributions, which we hope will provide new methods of analysis, extension, and insight. Thank you for your interest.